Welcome back to week 7 of the problem solving session for the Introduction to Fluid Mechanics course. I hope I'm audible, so someone can just give a thumbs up or type yes in the chat box. Okay, thanks, Saurabh. Okay, so I will wait for 2 more minutes to see if more students join, and then we'll start today's discussion. Okay, so I feel enough students have joined, so I think we can start. So this week, I'm sorry. So this week we will be starting the discussions on the dynamics of fluid motion. Fluid motion. So basically, we will be getting introduced to the fluid dynamics part of the course. So previously we were dealing with the statics part. We are seeing what are the forces that acts on the fluid and what governs the fluid characteristics in the case of fluid statics. And we saw that the forces that act in that case were the gravitational forces. Then we looked into the fluid kinematics part, where we considered fluid bodies into motion, and since we are dealing with kinematics, so we are not concerned with the forces that generate the motion, rather than we are more interested in the in understanding how the motion of fluid creates different kind of stresses and pressure differences in the flow. So, and for this part of the course, we are finally getting introduced to the dynamics part, where we will also, along with the motion of the fluid, we will also be concerned with the forces that generate this motion. So there was the concept of driving force, which I have mentioned in the first session, regarding the factor or the main source of the generation of this motion of fluid is known as the driving force of that particular flow. For example, in the case of pipe flow, the driving force is the pressure difference between the two ends of the pipe, or in the case of flow over a parallel plate, it's the inertia of the incoming flow. So these are the two main types of driving forces in the elementary kind of fluid flow studies. So in this case, we are dealing with the dynamics of in-viscid flow. Okay, so the word in-viscid inherently gives us an idea that we are dealing with fluid motions which are in-viscid in nature, or the kinds of fluid motion where the velocity gradients are considered to be negligible. Okay. So again, okay, so as per our usual agenda, I will briefly go through the concepts that were taught by Professor Chakraborty in the lectures. I will not dive deep. As you can see, I will sometimes skip some of the steps that were taken by Professor Chakraborty in the lectures, just in order to save time, because in today's session we have a lots of involving problems in this today's session. So I will prefer to give more time to those, rather than revising each and every steps that were taken by Professor Chakraborty. Nevertheless, I will go into the concepts which are more important to understand. Now, of course, steps are also important to understand, but I will just avoid it for the sake of saving time, because you can go back and see them in your notes or in the lectures. Okay, so with that overview, let's start. So we are starting with the Euler's equation of fluid motion. So I might have mentioned, and of course Professor Chakraborty might have also mentioned, that the governing equation for fluid motion in the case of in-viscid flow are the Euler's equation. Okay, the Euler's equation. Let me just write it. Euler's equations. Okay, so but similar, and these are for in-viscid flows. Okay, similarly, when we are considering viscosity or the viscous nature of the flow, then the governing equations become the Navier-Stokes equation. Okay, which we will introduce when we are dealing with the dynamics of viscous flows. Okay. So and since we already know that the concept of zero viscosity is not true. No, I will not say not true, but it's not practical, because there is no fluid in the world that has viscosity of zero. Okay, all the kinds of fluid flow that we see have some finite viscosity, because of which the velocity gradients are generated, and we inherently feel the motion of fluid over our skin, or say the drag because of the fluid motion over say aircraft or the vehicle that we are traveling upon. So we feel the presence of fluid, and that's inherently because of the presence of viscosity. Okay, but the primary question that may come in your mind right now is that if in viscid flows or fluids having zero viscosity are a concept that is not relevant in the practical perspective, then why study it? Okay, so the key thing to know is that for example, once we introduce you to the concept of viscosity, we will briefly discuss the concept of boundary layer. Okay, and boundary layer is something that I think we have discussed in our previous sessions, but we have not discussed the significance of the boundary layer theory. Okay, so the thing is that let me give you a brief overview so that you can appreciate the understanding of this concept of dynamics of in-viscid flow. Just to give you a brief example. For example, if you consider a flow or a flat plate, okay, say flow or a flat plate, I'm sorry. Okay, it's better. And this is the, say, the boundary layer that generates, and this would be the corresponding velocity profile. Okay, this is something that we have seen when we introduce the concept of viscosity. Okay, so it's again a good practice to go back and revise those concepts, because this is something that I really appreciate about the way Professor Chakraborty takes on his course. He basically discusses the entirety of the course in the very first lecture, and time to time he goes back to the concept that he had previously discussed, to give you an idea or a taste of what you know very little at the beginning, but once you go in depth, you start to appreciate those brief introductions that he had given in the start of the course. So with that similar approach, again I am coming back to the concept of boundary layer. So this boundary layer is generated because of the viscous nature of the fluid. Okay, the fluid tends, because of no slip boundary conditions, the fluids instead touching the upper surface of this plate will stick to this upper surface, and consequently they will try to slow down the upper layers of fluid motion, and then generate this velocity profile. Okay, but the thing is that the effect of the effect of the plate is actually being felt, or the significant effect because of the plate on the fluid motion is felt only to a very small finite area, because this is actually a very exaggerated version of the boundary layer. Okay, this is a very exaggerated version of the boundary layer, because in actuality, if you look into the boundary layer, say, let me draw a, say if you look into in the large scale, then the actual boundary layer will be something like a small region touching to the surface of the plate, and the rest of the flow that occurs above this plate can be effectively considered to be inviscid. Inviscid does not mean that the flow has zero viscosity. Okay, this is very important to know. That's why we preferably use the word inviscid flows rather than non-viscous fluids, because inviscid flow basically tells us that viscosity is very much present. Okay, mu is not equal to zero, but the velocity gradients that uh, generate the stresses are so low that we are not able to feel the presence of the plate, because in these regions the velocity gradients, such as, I will write only one example, say dou u by dou y, these are almost equal to zero. Okay, of course they're not zero, but they are almost equal to zero. That's why in this region can be effectively treated as inviscid, because the velocity gradients are absent. And since the inviscid nature of the flow governs a large region or area of large effective area of fluid motion around us. That's why it's very important to understand the fluid dynamics from the in-viscid perspective, primarily because uh, first thing is most of the flow field or the most region like common flow field that we see around us, the large area of those kind of flow fields are governed by the in-viscid nature of the flow because of the small scale of the boundary layer. But the other thing is that since we are neglecting the viscous terms, it effectively helps us to reduce the complexity in solving the governing equations. Of course, it does not help us tremendously in simplifying the governing equations because the main culprit in generating the nuisance of solving these kind of equations is actually the acceleration term, which is known as the uh, which is denoted by these terms. Okay, the product of the velocity with its derivative. So these are the terms that create the nuisance when we are trying to solve these equations analytically or numerically as well. Okay, but the absence of the viscous term in itself helps us to simplify the problem a bit more. That's why it's better to it's a good way to understand the fluid flow motions from the in-viscid perspective as well. Okay, so sorry for this long introduction, but I tend to do that just to be in line with Professor Chakraborty's vision of carrying forward the course. Okay. Okay, with that idea in mind, so let us again just simply consider this fluid element, small fluid element, and here now we'll consider the forces that acts upon it and then try to develop the governing equation that determines the motion of this particular fluid element. Okay, and again these derivations are done entirely by Professor Chakraborty very elegantly in these lectures, but I'll go through them once so that I can take out the governing equation which will deal again and again while solving the problems. So just consider this fluid element. We are considering a simple rectangular fluid element or a cubical fluid element considering the width to be unity to simplify the calculations. Then the pressure at the left hand side, the pressure force at the left hand side is given by P into delta y into delta 1 considering the width is 1, so delta y into delta 1 will be the area. I'm ignoring that into 1 factor. Similarly, the pressure force in the right hand side would be, I'm sorry, the arrow mark should have been in the opposite direction, so forgive me for that mistake. So it should be, pressure should always act inwards, right? So sorry for that mistake. Yeah. Pressure in the right hand side of the box is again given a P plus dou P by dou x delta x and delta y. So this part I will not go through again because this I have already discussed how it happens. It's basically a Taylor expansion of the pressure term at a distance of delta x from the left hand side, left end of this particular cuboid box. Then sorry, then the body force at x along this fluid element is given by rho into bx into delta x and delta y into 1 to consider the volume of the fluid element. Okay, so just 1 second. Yeah, so doing the force balance along the x direction, the summation fx is equal to delta m into ax. For this particular fluid element, we will have p into delta y minus p plus dou p by dou x into delta x, sorry, into delta y plus rho bx into delta x into delta y would be equal to this delta m into ax, where ax is given by this term which we have thoroughly discussed where we are discussing the fluid kinematics part, the expression for acceleration along the x direction or the x component of the acceleration, okay, or the component of acceleration in the x direction. Okay, so I think you are well versed with this expression, and the volume is again given by mass is given by density into volume, so volume would be delta x and delta y into delta z, where delta z in this case is 1. Okay, so now if you simplify this expression, what we will left with is this form of the equation, which is minus dou p by dou x plus rho bx is equal to rho dou u by dou t, rho into dou u by dou t plus u dou u by dou x plus v dou u by dou y plus w dou u by dou z. Okay, so this is the Euler equation along the x direction. So similar expressions can be obtained along the y and the z direction as well, given that we are considering a Cartesian coordinate system, and you can again obtain the sorry for this noise. You can obtain the corresponding equations along the y and z directions as well. Okay, and there are some specific terms, specific names given to these each and every terms here. So the first term, dou p dou x term, is the pressure forces that act on the fluid element. Then there are the body forces. So again, these pressure forces are the surface forces that we discussed previously, the two types of forces that act on the fluid element, and the body forces are given by this term rho bx. Okay, and the term on the right hand side is the inertia term. Okay, because it contains derivative of it, the rate of change of velocity, or the acceleration term, so it comprises the inertia term. Okay. So now let us take an example of a particular type of flow and then try to obtain the expression for pressure distribution, given that the velocity profile or the velocity field is given, that is v is equal to ax ik minus ay jk, and given that gx along the negative z direction, obtain the expression for pressure. Okay, so we need to find the expression for pressure, how the pressure varies given that we have the velocity field in our hand. So if you try to approach the problem mathematically, the thing will come in mind is that we have this governing equation. Okay, and in this case it's a 2D flow because there's only two velocity components, so this term you can neglect for now. So you will be left with one equation along the x direction, dou p by dou x plus rho bx equal to rho dou v by dou t plus q dou v by dou x plus v dou v by dou y, and the other equation will again be the same equation along the y direction. It will be minus dou p by dou y plus rho by is equal to rho dou v by dou z plus u dou v by dou x plus v dou v by dou y. Okay, so you are left with two equations. Okay, two equations along one along the x direction and one along the y direction, and the known terms that you have are the u component of velocity and the v component of velocity. And say if rho is constant, then say I'm just giving an approximation. If rho is constant and given that body force term is also given here, then you need to find the expression for p. So basically, if you take this term in the right hand side, you just need to integrate this term to obtain the expression for pressure. Of course, you need to do it for both the x direction as well as the y direction, and then compare the terms. That's something that we did while we were dealing with the stream function, and then find an equivalent expression for pressure. Okay, so is it clear till now how to deal with this kind of problems given the velocity field, how to obtain the pressure? Someone can give a thumbs up, yes, no. Thanks, Saurabh. Others, could you understand, or should I repeat it? Otherwise, I'm going through this problem anyways because it's something that was done by Prof. Chakraborty, so we'll get to know a bit more clearly. But okay, then if that's the case, then I will just continue. Okay, so as I mentioned, the governing equation is the Euler's equation of motion, because let me just explicitly mention it here as well. The flow is in viscid flow. Okay, the flow is in viscid flow. So we take the help of the Euler's equation. Okay. Or in other words, if I would like to add one more thing, like again, as I mentioned, like if you don't know anything, say if you're just stuck in a problem of fluid mechanics, then as I mentioned, apply the continuity equation, the momentum equation, and the energy equation. So in this case, since temperature is not mentioned, so we are only dealing with continuity and the momentum equation. So since continuity equation won't suffice because you need to find the pressure, and the pressure is contained in the momentum equation term, so we can start with the momentum equation which will all inherently have the viscous term. But since the flow is in viscid, we will again just come back to the Euler's equation of motion. Okay, I'm just telling you the solution methodology of these kind of problems. Okay, how to think while solving this kind of problems. Okay, so for the equation along the x direction, I have dou p by dou x plus 0 because there is no body force along the x direction, so it is dou p by dou x plus 0. And I think I have to zoom out a bit so that I have this equation in mind. Okay, so I have these terms. So the flow is steady because the velocity profiles do not, or the velocity field does not depend on time. So this term is absent. So you are left with these two terms. Okay, so u is ax, substitute by a, and dou u by dou x would be a dot a plus this term dou u by dou y would be 0 because a depends on your x, so this is 0, and similarly since z component is 0, so this term will also be 0. Okay, so we'll be left with dou p by dou x is equal to rho a square x. Okay, minus dou p by dou x is equal to rho a square x. And if we integrate it, we will be left with p is equal to minus rho a square x square by 2 plus some function of y and z plus some arbitrary constant. Okay, similarly along the y direction I have minus dou p by dou y plus 0 because body force along the y direction is 0 because gx along the negative z direction as it is mentioned here. And again similarly we have rho, you will be have I will just write the equation to remove any kind of confusion. So along the y direction the only equation would be dou p by dou y plus rho by equal to rho dou v by dou t plus u dou v by dou x plus v dou v by dou y plus w dou v by dou z. So, okay, so a good practice is to write the entire equation and then remove the terms that you know that would be 0, so that you miss the, so that you can avoid any kind of terms that you might have missed while approximating it in your head. Okay, so it's just better to write the entire equation beforehand. So this is 0, so this term would be 0. Flow is steady, so this term is 0. Again body force on the y direction is 0, so this term would be 0. Okay, so we only left with 3 terms now. So it's dou p by dou y as it is written here. Then u dou v by dou x. Okay, so dou v by dou x is 0 because v is a y, only a function of y, so this term is 0, so this will again be 0, so we will left with only this term. Okay, so v is minus a y, you can write minus a y, but again dou v by dou y would be minus a, so minus minus will cancel out, so we will left with a square y. Okay, so we will left with minus dou p by dou y is equal to a square y. Okay, again once you integrate it, you will be left with p is equal to minus rho a square y square by 2 plus some function of x and z because it's a partial derivative and a arbitrary constant c2. Okay, now similarly if the body force was not along the z direction, we could have just left the equation of motion along the z direction, but since there is a body force along the z direction, it will contribute to the expression for pressure. Okay, because we saw that in fluid statics as well, when there was a the gravitational force was acting in the case of fluid statics, even if there was no velocity components because it was basically a static flow, there was a pressure gradient because of the depth of the flow because of the presence of the gravity. Okay, applying same concept in this case. Again, you will just boil down to the equation of fluid statics here because there are no velocity components involved. So dou p by dou z minus rho g because the body force is minus g in negative z direction, and the right hand side will be 0 because all the velocity terms here are 0 because it will all the terms will be multiplied by w dou by dou t plus w dou plus u dou w by dou x plus v dou w by dou y plus w dou w by dou z. W is 0 in all the cases, so this entirety term would be 0. So you will only be left with this left hand side. So once you integrate it, you will get some terms like p equal to minus rho g z, some function of x and y plus a constant c3. Okay, so again there was again a step-by-step method to approximate the terms, but what I did was I used my way to deal with this particular problem. So what I did was I am just comparing now these 3 terms. Okay, all these 3 terms are the same pressure that we need to evaluate, so we just need to compare these 3 terms and see which are terms we need to keep and what we can avoid. Okay, so let us look into this expression. Okay, so here we have minus rho gz plus some function of x and y. So what can be those function of x and y? So let us find the function of y first. So once you look in the second term, we have a function of y, minus rho a square y square by 2, but the function of x is missing, but the function of x is there in this term, and function of z is already considered in this term, so we need to look for the function of x now. Okay, so once again let us go back to the previous term. We have a specific function of x minus rho a square x square by 2, and this is now, and the expression from y is included here, and the function from z is included here. So all the terms are included while we are comparing the partial derivative functions. Okay, so this term, and this term will have to be there to satisfy this condition that all these three pressures are the same, plus an arbitrary constant that will remain same for all the cases. So comparing all these terms, we will be left with P is equal to minus rho a square x square by 2 minus rho a square y square by 2 minus rho gz plus some arbitrary constant c. Okay, then if you take all these terms to the right hand side, the negative terms to the left hand side, I'm sorry, we will left with P plus half rho v square. I will come to how we came to v square plus rho gz. So v square actually comes from the fact that this a square x square actually, like, if you take, I'm going there. Okay, if you take the modulus of this term, then you will be dealing with the magnitude of this term. So say something like u square plus v square, it will be again ax whole square plus ay whole square. Okay, magnitude of this term. Okay, then if you take the square of this term, then it will be modulus of v square would be just v square, it will be equal to a square x square plus a square y square. Okay, so I hope you knew it already, but I'm just revising it once again just to remove any kind of confusion. So with this analogy, we can reduce this term as minus rho v square by 2. So it will go to right hand side, it will become half rho v square plus rho gz, it will remain the same, and it will be equal to some constant. And this equation, P plus half rho v square plus gz is equal to c, is a very, very famous equation in the case of fluid mechanics. It's a very popular equation. So this equation is known as the Bernoulli's equation. Okay, again we will dive deep into the entire derivation of the Bernoulli's equation, its specifics or the assumptions that are required for the validity of the Bernoulli's equation, because this is an equation of, although it's very famous, but it's a very specific equation because we can only apply it to very certain specific cases. Okay, that's why it's very important to know about the factors that are required for the validity of this Bernoulli's equation. And in fact, in many competitive exams such as GATE and ESE, or even in your interview questions in your colleges, these assumptions are most of the times asked like again and again, like what are the assumptions that are required for the validity of the Bernoulli's equation. So I will give you my experience. In fact, during my interview, I was also asked the same question: what are the validity required for the Bernoulli's equation? Okay, so just to give you the importance of those assumptions, let us now we'll go through it very thoroughly. Okay. Then again, then we just saw that this flow is, there are no viscous effects in this kind of flow because the velocity gradients are strain-rate tensor gives equal to 0, then the angular velocity is 0, the flow is irrotational as well, and the divergence of velocity field gives us 0, which tells us that flow is incompressible. Okay, so I guess remove this, the equation of streamlines. If you want to go, it's just like if you want to, if I just a detailed analysis again after done by Professor Chakraborty to just again take most out of this particular problem. So again he shows say let us find the equation of streamline for this particular problem. So it is again dx by u plus is equal to dy by v, then dx u will be ax and v will be minus ay. So if you simplify this equation, a will be cancelled out from both sides, we will be left with a very simple equation xy equal to c, and this particular form of the equation is also very popular. So these kind of equations, let me just write it just for your knowledge, you can remember, are known as rectangular hyperbolas. Okay, I think Professor Chakraborty might have mentioned, but I am just reiterating it. Okay. So this rectangular hyperbola becomes quite relevant when you, or is relevant also in the case of very famous equation known as PV equal to C. So for it's a pressure volume relation in the case of isothermal flows. Okay. So the pressure volume relation generates an rectangular hyperbola in the case of isothermal flows. Okay. And just an additional fact to remember, because in the later part of today's session, say in the problem solving session, you will be given a question that is related to isothermal flows. Okay. Of course, not from a thermodynamics perspective, but from a fluid mechanics perspective. But just to give you a brief idea, I'm introducing this. Okay. Now let us come to the main topic of discussion. That is the Bernoulli's equation. Okay. So just give me 1 second. Meanwhile, you can just try to digest whatever we have discussed till now, and then we will be directly going to the derivation of the Bernoulli's equation. Okay. Okay. And so moreover, it seems that uh, if I go with this space, we may be short in time to solve the problems, because they are going to take a bit more time this today. So let us. So what I will do is, if everybody is all right, I will try to quickly go through the steps. Okay. Of course, I will go through each and every step quite as nicely as possible, but I may go a bit quick just in order to save time for the problems part. Okay. Because this derivation, of course, is done very beautifully by Professor Chakraborty, so you can go back to the lectures to understand the derivations. But in order to save time for the problems, I'll maybe go a bit fast. I'm sorry for that, but again, if you have any doubt, you can stop me. Okay. So is that alright with everyone? I may go a bit fast, but I would like to compensate it in the problems part. Okay. Is that okay? Yes, no, thumbs up, anything? I'll wait for. I cannot wait. In fact, we don't have time. Okay then. If nobody is responding, okay. Thanks, Mangal. Thanks. Oh, I think I can go, because this derivation you can again revisit the lectures. So I'll go a bit fast. Okay, but sorry for this thing. So sir, I have doubt regarding vector identity used in term 2. Okay, we will reach there. It is something that I have also taken from the lecture videos as sorry, Divyanshu wants to join. Okay, so sort of this is something that I have taken directly from the lectures. So if you have any doubt regarding the identity, that I do not know, but if there's doubt regarding the calculation, you can ask. But this is something that I have directly taken from the lectures. Okay, we can discuss while we reach here. Okay, so let us try to go a bit fast. Okay, so we are trying to solve the equation of motion along a particular streamline. So let us consider a particular line element along which we want to do the analysis. So the line vector is given by dl is dxik plus dyjk plus dzkk. Okay. Oh, sorry. Just to before the why we are dealing with streamlines, because this one of the important assumptions of Bernoulli's equation is that this term is a constant. Let me go back. I'm sorry. This sum of p plus half rho v square gz is equal constant is constant along a streamline. Okay, it's one of the very crucial assumptions. Along a streamline. Why it's along a streamline, that also we'll understand after we do the derivation, but that's the case. And if the flow is irrotational, then this equation becomes valid for any 2 points in the flow field. Okay, it might be a bit confusing, but these are the specifics that I need to mention. Okay, that's why we are starting with understanding the fluid motion along a particular streamline. Okay, so let us consider a particular line element as dl is equal to dx I cap plus dyjk plus dzk cap. Then say dp, if p is a function of x, y and z, then dp will be given by dou p by dou x dx plus dou p by dou y dy plus dou p by dou z dz. Okay, and the advective term, okay, or the advection term, basically the acceleration term in the inertia term is given by this particular expression. Okay, it's basically the right hand side of the equation. It is minus rho dou by dou t plus u dou by dou x plus v dou by dou y plus w dou by dou z plus rho bx dx. Okay, it's along the x direction. Okay, so if we consider all the terms together, like all the coordinates together, then in general we can write it something as dp would be equal to minus rho dou u by dou t dx plus dv by dt dy plus dw by dt dz. Okay, and then the second term would be minus rho v dot delta v dot nebula u dx plus v dot delta v dot nebula v dy plus v dot nebula w dz. Okay, and the body force term would be rho dx dx plus by dy plus dz dz into, sorry, it will be the term 3. Okay, so term 1, if we just simplify this, like if you want to write this, is there any more comment? Okay, we'll reach there. Okay. Yeah. So yeah, so if you want to write this term, particular term in the, just give me 1 second. Yeah, so if you want to write this term in the vector form, then it will basically be rho times dou v by dou t dot dl. Okay, when dl is given by this expression, you can just see it, the dot product between these two, this and say the dv by dt will give you this expression. Okay, because either I cap will be 1, 0, j cap will be 1, k dot k will be 1, so you will just boil down to this particular expression. Similarly, this term 2 can be written as v dot nebula over operating over v, there is a velocity vector dot dl. Okay, and finally the term 3 would basically be rho g into dz, because if we consider the body force to only act along the z direction, negative z direction, so only this will be equal to minus g, these two will be equal to 0, so it will be minus rho g into dz. Okay, shown here. So yeah, let me ask, I do not know whether I will do answer it or not, but what's the doubt in term 2? Like this is a vector identity, that is just what to say, I just took from Professor Chakraborty's lecture. So you have any doubt regarding this identity, like how this identity is obtained, or is it something else? Saurabh? Like how this identity is obtained. Okay, so the thing is, I also am not well versed right now to derive this entire expression, but what I can say is right now you can just take it like it, what it is. But one thing you can do, like if you are concerned regarding the validity of this particular identity, what you can do is, see, you have this identity here, right? And you have your velocity as say ax I cap minus ay j cap. Say this is your velocity. Okay, so with that thing in your head, what you can do is you can substitute this particular expression for the velocity vector in this identity and try to see whether this condition is satisfied or not. Okay, and then at least in one way you will understand that this vector identity is valid. Okay, but other thing regarding the derivation, it's something that right now I will not be able to do. So what I can do is, sort of like, if you are joining the next week, just before the start of next week's session, what I will do is I will take the entire derivation of this particular identity for the first say 2-3 minutes to show you that, and then we can continue next week's discussion. Would that be fine? Okay, yes, thank you for the understanding, but okay, it's a valid doubt, but right now I do not have the derivations with me to derive this identity. Okay. Okay, so with that discussion, so as Sora was mentioning, so we have this term in our hand. Okay, so we want to simplify it, and there is a very famous, actually very famous vector identity given by these relations, and substituting the value of v dot nebula v, by this we can get the term 2 to be minus rho half nebula operating over v dot v minus v cross the vorticity dot dl, that will remain as such. And since okay, I will keep it right now because we have not till said that the flow is irrotational. Okay, so again let's go down. Then what we can do is we can simplify this term to a bit more to get a much more relevant term that because we want to simplify it so that we can get a term that is quite familiar, that we are quite familiar with. Okay, basically we are trying to obtain the Bernoulli's equation, so we need a term that we are quite familiar with. Okay, so what is missing is, if you just go back, so the pressure term is itself in the right hand side, in the left hand side, so that's already there. The body force term that comprises the gravitational or the potential energy term is already there. So the only term missing right now is the velocity term or the kinetic energy term. So we need something familiar term that we need to derive it accordingly so that we can obtain the kinetic energy term. Okay, so that's something that we should keep in our mind while deriving this expression. So the term that can possibly give us the kinetic energy term is this particular term, because v dot v will just boil down to v square. So with that idea in mind, let us try to simplify it even further. Okay, so this is the vector identity. Okay, again valid for any kind of coordinate system, but say we are dealing with a Cartesian system, just to simplify our calculations, because this should be valid for any kind of coordinate system. If you want, you can do it for cylindrical or spherical coordinate system, but since the Cartesian makes it a much more simpler derivation because of the absence of any kind of coupling between the coordinates, so we use the Cartesian coordinates. Okay, and so this term would be again half times nebula operating over v dot v. V dot v again boils down to v square. Okay, where here v square, just to make sure you are not confused with it, v dot v would basically mean u square plus v square plus w square. Okay, so this v is small and this v is capital. Okay, which is indeed equal to the modulus of v square or just capital V square. Okay, that is the square of the modulus of the velocity. Okay, the velocity vector, not the y component of velocity. Okay, not to get confused with that. Okay, so this v, okay, I think the way I write might create confusion, but this v is indeed the capital V. Okay, not this y component of velocity. Okay, so v dot v would be square of the modulus of the velocity vector. So we can add I dot dx, because if this operates on, sorry, if this nebula term operates on v squares, it will be something like this. Okay, so this v dot v will just boil down to a scalar, because this term do not have any this I cap, j cap, k cap term. So this is a scalar. Okay, and this term basically the gradient of the square of the modulus of the velocity vector. Okay, and where this term is a scalar. So I by dou x over operating over v square, j cap dou y operating over v square plus k cap dou y operating over v square, where v square is this. Then again multiplied with this term, that is dot dx I cap plus dy j cap plus dz k cap minus this term that we already have in our hand. Okay, we will leave it as such because we want to take a particular approximation that will avoid this term completely. Okay, again if you simplify it further, you will be left with again a simple dot product between two vectors. So this will operate with this will operate with this will operate with this. Then we will be left with rho times half dou by dou by dou x of v square dx plus dou by dou y v square dy plus dou by dou z v square into dz minus this term that is left as such. And this term, if you see, is basically the complete derivative of this scalar v square. Okay, something similar to what we have done here. If I go back here, so if you just substitute p by half v square in this expression, this expression will exactly get this term. So it's basically half of d into v square, with dv square denotes a complete derivative of the square of the modulus of the velocity vector. Okay, then just simplify it a bit further, so we will be left with half rho dv square plus minus will add up, so it will be plus rho v into the v cross the vorticity vector dot dl. Okay, now if we combine all these terms now, you will left with dp is equal to minus rho dou v by dou t dot dl minus half rho dv square plus rho dl dot v cross vorticity or v cross omega minus rho g into dz. And then again, if you rearrange these terms, you will be left with dp plus half rho dv square plus rho g dz plus rho dou v by dou t dot dl minus rho into dl dot v cross the vorticity omega. Okay, so up to these terms, like if you just try to visualize it at least, you will see that these first three terms are quite familiar to the Bernoulli's equation that we know very well. Okay, so it's just you can see it's just the integration of these terms, you will get the Bernoulli's equation, right? But the other two terms, unsteady term and the vorticity term, are inherently present when we start with the Gaussian equation of motion, the Euler's equation. But there are certain criteria or certain approximations that we can make that will help us to avoid these terms. Okay, for example, if we consider the case like if we just take the cross product, or if we just simplify this term, it's basically the scalar triple product of dl, v and omega. Okay, so I will just write the term. I will leave you as an exercise to understand what is a scalar triple product. Okay, just to be sure. Okay, then sorry, if you simplify this product, we will be left with the dl, the first vector would be in the would be in the first row, and the other two cross productors will be in the other two remaining rows. Then if first thing is, if the velocity vectors, that is u, v and w, are along the line element that we have chosen initially, that is basically the streamline. So if they are parallel to each other, or basically if the velocity vectors are along the chosen line element, then this term would be equal to 0, right? Because these two terms become the scalar multiples of each other, then this term becomes 0. Okay, secondly, this term can also become 0 if the flow is irrotational. Basically, if this term is equal to, say, del cross v is equal to 0, then this term will be equal to 0. So this whole term becomes equal to 0. So we are only left with these 4 terms. Okay, so the term a, this term a can be 0 within these 3 circumstances. First is the one that I have already discussed. If dl is along a streamline, basically dl is a streamline where u, v and w, where the tangent to that particular line will give us the velocity component. So in that case, these two terms become the scalar multiples of each other. Then this term becomes 0. Secondly, if the flow is irrotational, that is this term is equal to 0, then this term can be neglected. And finally, other special case, very special case, is that if dl and v cross omega are perpendicular to each other, like given that this is not a streamline and the flow is rotational, but if dl and v cross omega are perpendicular to each other, then dot product of these two perpendicular elements would give us 0. Then also this term can be equal to 0. But this case, this final case, is very very specific, which is very hard to generalize. So this condition is usually neglected, but this condition still remains. Okay, it's not that it does not remain, but it remains, but it's very very specific, so it's not valid. It's not, I would say, quite, it can be not quite generalized. Okay, but these two conditions can be generalized, so these two terms or these two cases are quite popular to know. Okay, so as I mentioned, like, then now one more approximation that you can do is that if you now consider the flow to be steady, okay, consider one more assumption. Let me just write those assumptions that we are taking right now. First is, we can take flow is irrotational, just so that we are left with these three terms. Okay, first is, if we if the flow is irrotational, then we are left with only 4 terms, the first 3 terms and the unsteady term. Then if the flow is along a okay, let us say also that flow is along a streamline, then also we can neglect this term. Okay, one is if the flow is steady. Now if the flow is steady, then also we can neglect this term, so that only these 3 terms remain. So these are the assumptions that we have got till now, okay, that we have to take to simplify this particular expression. Okay, so let us now look back. Okay, so now if I take the flow to be along a streamline and a steady flow, okay, so along a streamline, then this term will go away, steady flow, this term will go away, so we are left with these 3 terms. So we are left with dp plus half rho v rho dv square plus rho g dz is equal to 0, which is the Euler's equation of motion along a streamline. Okay, it's not yet the Bernoulli's equation. Okay, because for Bernoulli's equation there are certain assumptions that need to be satisfied, which we'll eventually see. So we are left with, now if we apply this equation along 2 points along a streamline, okay, 2 points can be anywhere, but those 2 points have to be on the same streamline. Okay, same streamline, along the same streamline. Then we can write it as, we can take density as a, if we divide all the terms by density, so we want integrating over 1 to 2, 0.1 to 2 dp by rho plus integrating from 1 to 2 half dv square from integrating from 1 to 2 d into dz, okay, which is equal to 0. Now if we assume rho to be constant, okay, one more assumption. If we take rho to be constant, let us write it here, rho is equal to constant, and again rho is equal to constant does not mean the flow is incompressible, but it is a very incompressible flow, but a very specific case of incompressible flow. Okay, so now if I finally assume that rho is constant, then I can take rho out of the integration, so we can write it as p2 minus p1 by rho plus half v2 square minus v1 square plus g into z2 minus z1 equal to 0, which now is the much celebrated or much popular Bernoulli's equation. Okay, so these are the exact 4, and again the flow is inviscid because let us go back again. Sorry, I forgot the most important assumption. The flow is inviscid because we are still starting with the Euler's equation of motion. So these 4 assumptions are the exact assumptions, 5 actually, will come to the rotational part. So these 5 assumptions are exactly the same assumptions that are mentioned here. So for the Bernoulli's equation to be valid, these are the assumptions that need to be there. Okay, first is the flow is inviscid because we are starting with the Euler's equation of motion. Second is the flow has to be steady. Okay, again there is an unsteady form of the Bernoulli's equation as well, where we can simplify these equations, but we have to leave this unsteady term intact. Okay, I guess we will deal with such kind of problems in the coming week, but right now we can just say that it exists. So there can be an unsteady form of Bernoulli's equation given that we leave the unsteady term there itself. Then rho is equal to constant, which is a very special case of the incompressible flow. But this rho equal to constant is not required for the Euler's equation of motion. Okay, because the flow has to be incompressible, of course, in Euler's equation, but need not to be, but it does not require rho to be constant. Okay, you already dealt with that part where the flow is considered incompressible but rho is not constant. And finally, the flow has to be along a streamline. And this condition, now coming to a very important point, that this condition of the Bernoulli's equation to be very along a streamline can be relaxed if the flow is irrotational. Okay, so usually if I say that I am applying this Bernoulli's equation along a particular streamline, okay, say point 1 and 2 which are along the same streamline, so but I can now consider these 2 points where I am applying the Bernoulli's equation to be at any 2 positions in the flow domain, given that all the 3 assumptions are satisfied plus the flow is irrotational. Okay, so I hope this is clear, because very crucial fact that one needs to know. Okay, so with that I think should I go okay, I think that with that I can leave the theoretical discussion part, and then I can now directly go to the problems. Okay, so I hope this is clear till now. Okay, thanks Saurabh. So let us go to problems, and today's problems will be quite involving, and you need to do the calculations and tell me the answer. Okay, so let us, I hope the questions are visible. Okay, so let us start with the first question. Which of the following, let us start with the first question. Which of the following is true, okay, is true with regard to the Euler's equation of motion? Okay, first is it does not consider the body forces acting on the fluid. Second is it is very only if the fluid is viscous and steady. Third is it is based on conservation of momentum for an inviscid and incompressible flow. Finally, it is based on the conservation of mass for an inviscid and incompressible flow. So which is the correct option? Very simple. Okay, Ketan says it's C. Others, can you give your opinions? So today's session will be quite involved, so I would request that students try to reply a bit fast, especially when we are dealing with this. Okay. Okay, Saurabh, you have any doubt? You can unmute yourself and ask.
Sir, we did not assume any incompressible flow regarding Euler's equation of motion.
Yeah. Okay. So let me go back. Yeah, but if the flow is not incompressible, then we cannot take, at least in this, okay, let me just specify correctly. For this condition, this equation, for rho to be taken out, we have to implement the incompressibility condition, right? Then only we can take rho out of this, rho out separately. Okay, let me just try the this. Okay, it's a valid doubt. I will just try to understand from the mass conservation. So it would be so dou rho by dou t plus v dou. flow, and this should be du by dt plus rho. Okay. So it's a very valid doubt, because indeed Euler's equation of motion at least can be approached from the case where flow can be compressible, but at least from the with the uh, with the derivation that we have done till now, the the with that idea in our head, which of the following options seems to be more, which seems to be the most appropriate one? Okay, that we can choose. Just you can go to try to answer it. Ketan says C, but I will try to just what to say, confirm it once. You can just tell me the answer. Okay. Meanwhile. Just 1 second. Okay, so I will get to that part. Meanwhile, let us try to look into question number 2. Okay, I hope that's okay. I'll get back to question number 1, but let us try to look into question number 2. It's a valid doubt, but let us come to question number 2 for now. Okay, the velocity field for an in-viscid two-dimensional incompressible flow. Okay, there are a lot of assumptions to take into consideration. It is in-viscid two-dimensional and incompressible flow is v equal to ax I cap minus ay j cap. Okay, so yeah, and it is given, the velocity field is given by ax I cap minus ay j cap. Okay, it's very simple velocity field. A is 0.3 and second inverse, and g is minus g j cap. Okay, considering the fluid to be water of rho s equal 1000, find the pressure difference between the points 1, 2 and 3, 5. Okay, A and B. So I hope the question is clear. So I will just give one hint. Start with the Euler's equation of motion. Okay, since you are dealing with 2D flow, so along the x and y direction, I'll give you the steps. You can do the calculation. Then try to find the expression for pressure. Okay, and then find PB minus PA. Okay, you need to go through these steps in order to find. You cannot apply Bernoulli's equation here, so you need to go through these steps. Okay. Meanwhile, I'll just try to look into question number 1. So, because it's something I myself had a bit of confusion, but how to explain it. But let's try to look into it. Okay. So yeah, please try question number 2. It's a bit more involved than other previous week's questions. So I'll give you, say, 6 minutes. You can try it, and then we'll look into the solution. Okay, sounds fine? Please try question number 2. Okay, meanwhile I'm going to question number 1. So Okay, Saurabh again. Uh, Saurabh, is there any doubt in this question? You can unmute and ask. Your raised hand, it seems, or it was a previous one. Okay. So, one more minute, then we'll look at a solution. One more minute. Anybody, will you give it a try? Okay. So, I think we have to start with it. So, let us look in the solution. Okay. So, for the first question, it was Saurabh, I guess. Uh, see, the doubt is very quite valid. So, given that there would have been an option of say none of these, then this would have been the correct answer. Okay, but as I already mentioned, apart from the fact that it can also be validly applied for compressible flows, because it is the governing equation of the case when we are dealing with equation of motions in the case of compressible flows. Okay, so all the governing equations in those cases are initially derived starting with the Euler's equation of motion. But from the case that we have been studying till now, the most suitable answer in this case would be option number C, as Ketan rightly mentioned. Uh, and one more thing that can give you an idea is that if you are solely, let us go back to the notes once. See, if you are solely dealing with this equation, okay. See, if you are solely dealing with this equation to determine the net forces that acts on the body, or basically find the expression of pressure, because this is the pressure in this case that will drive the force, as well as the, of course, the body forces. So these two will drive the force, and this term is usually known. So the only thing that you need to find is the pressure force term, because it is in terms of the pressure gradient. So you need to find it. So if this is a sole equation that you are using to find the net forces that act on a body, in that case the flow has to be incompressible. Why? Because if that's not the case, then this equation will become coupled with the mass conservation. Okay, so these two equations has to be solved simultaneously to find the expression for density, because density is now also varying with the, say, space or time. Okay, so with that idea in mind, okay, and these are the cases that occur, because in that case when density is varying with say is a variable, then we have to take one other equation, that is the equation of state, that P is equal to rho RT. Okay, so we need to again take the help of this equation to find an expression for density, and then solve the Euler's equation of motion accordingly. Okay, that I was eventually seeing. So Saurabh has rightly mentioned the case that Euler's equation of motion is valid for both compressible and incompressible flows. But given the scenario that among the following options, the most suitable answer is option number C. So we have to go with option number C, because Euler's equation of motion is the conservation of momentum for in viscid and incompressible flow in the simplified case that we have studied till now. Okay, but in a general case, Euler's equation of motion is valid for compressible flows as well. Okay, but since it is not specifically mentioned among the options that we have in our hand, so we cannot go with this. So right now we have to go with option number C. Okay, so is that fine, Saurabh? Thanks for pointing it out. Actually, I appreciate that, but I just skipped that part because I thought it would not be required, but it's nice that you're pointing it out, so it is helpful for others as well. Okay, thanks for that. So let us go to question number 2. It is a Saurabh says 1305 Pascal. So I think it's correct. Magnitude seems right, but I think there might be a sign change because of it is PB minus PA or PA minus PB. Saurabh, what have you obtained? PB minus PA or PA minus PB? That also matters.
Sir, PA minus PB.
Then it's correct. Okay, so but okay, I asked P minus PA, so it will just be -1. So this is correct. Thanks, Saurabh. So Saurabh was able to obtain it. So let us just look into my solution. Actually, it will just be the same thing, the step that I mentioned here, but just for the sake of helping others as well, if you are stuck at somewhere, you can just follow the steps that I have used. Okay, so yeah. Oh, I missed a very crucial, but I'll just go through it once. Okay. Yeah, so we have Q is equal, the question is V is AXIK minus AYJK, and A is 0.3 second angle, G is minus G JK. Okay, it is 2D in viscid incompressible, so we cannot apply Bernoulli's equation right now. So we start with the Euler's equation of motion along the x direction. We have dou P by dou x is equal to minus rho U dou U by dou x plus V dou U by dou y. I have neglected the unsteady term because the velocities are not depending on time, so I have just disregarded the unsteady term in both the cases. Okay, just to not be confused. Then just substitute the value of U and V here, so you will find that this term is 0 because U is only a function of x, right? So we will left with dou P by dou x is equal to minus rho AX dot A, because dou U by dou x would be A. Once you integrate it, you will left with P is equal to minus rho A square x square by 2 plus some function of y. Okay. Similarly, if you write the Euler's equation of motion along the y direction, you will have dou P by dou y plus rho g, because now body force term is there, minus rho into U dou V by dou x plus V dou U by dou y. Okay, I've just shifted the minus sign from the left hand side to the right hand side. So we will left with minus dou P by dou y is equal to minus rho. This term would be 0 because dou V by dou x is 0. So minus rho. So we left with this term. So V is minus AY and dV by dy is dou V by dou y is minus A. So we left with dou P by dou y is equal to minus rho A square y minus rho g. Okay. Once you again integrate it, you will left with P is equal to minus rho A square y square by 2 minus rho gy plus some function of x. Now if you compare both the terms, equation 1 and 2, you will be left with P is equal to minus rho A square by 2 x square plus y square minus rho gy, and plus some arbitrary constant if you want to keep. I'm sorry, but okay. But again, using the appropriate boundary conditions, you can just say that I am considering C to be 0 as a datum. Okay, so it's something that is being practiced by Professor Chakraborty. Okay, just simplify the case, because now again, if you just, even if you keep it, say, if you subtract it, say P2 minus P1, this both the constant will get subtracted. That's another way to cancel it out. It will eventually get cancelled out. So the only term that will make difference is these two terms which depend on x and y. Okay, so given that a is equal to 1 and 2, b is 3 3,5, and rho is 1000, and a is 0.3. If you substitute those values, you will get pb minus pas minus 1305 Pascal. Okay, I hope it was clear. So now let us look into the next question. Okay, yes, Saurabh, you can ask.
Sir, regarding the solution, okay sir, G is in minus G direction.
Yeah, so
minus J cap.
yeah, so it was minus, it will also be minus. I just took minus in this side, so it will become, both will become plus and this will become minus. Is that fine?
Yes.
Okay, thank you. So let us look into the next question. The question number 3. So we have considered the following equation, then the statements are given after. So this is the Gaon equation, and it's something that you are quite familiar, you just dealt with it. So the statements are steady flow in viscid flow. I should remove this. Steady flow in viscid flow, gravity as the only body force, incompressible flow in rotational flow. These are the statements. Okay, so the question now is, I think I have to zoom out. It is in the next page. So the question, which of the following is correct for the given equation? Okay, so the question is, which of the following assumptions are correct for this particular governing equation? Okay, so I will, since in the next page, I will just write the options here, so it is helpful for you. So A is 2, 3, 4 and 5. B is 2 and 3. C is 1, 3, 4 and 5, and D is 2, 3 and 5. So which of the following statements are correct for this particular form of the governing equation? So we dealt thoroughly with the derivation of the boundary equation. This is one of the steps, preliminary steps, I will say penultimate steps before reaching the final form of the governing equation. So which of the following statements are correct, or assumptions are correct for this particular form of the governing equation? Okay. Saurabh says it's D. So he says the flow is inviscid. 3 is gravity is the only body force, of course. And 5, flow is irrotational, because we are not having the other term. It is this term, right? dl dot this term. So actually it is correct, because flow cannot be steady because we are having an unsteady term, so this is wrong. Flow is inviscid because there is no mention of the viscosity here, so flow is inviscid, so this is incorrect. Oh sorry, this is correct. Gravity is not only body force, because the only body force that acts in this particular equation is the gravitational force.
Why you have mentioned steady force is incorrect?
What? Steady flow is incorrect? Oh, because this term is there, right? Is it clear? So dou by dou t term is there. It is contributing to the governing equation, right? So this is non-zero. So flow cannot be steady, right?
Okay, sir.
Okay. thank you. Yeah. So gravity is the only body force because there is no mention of other types of body forces such as electromagnetic forces or or other types of or magnetic forces. So this is the only body force here. Okay, or electric potential. These kinds of force are not mentioned. So the only body force is the gravitational force here. Okay, then so this is correct again. And of course incompressible because we are not having to deal with this term. Sorry, this term here, right? There was a, if I go back, so there was this term. If you go back here, this term, right? This term is absent in this case. Plus the right hand side also is 0 in this equation. Okay, so we are not having to deal with this kind of terms. So the flow is irrotational. Okay, has to be rotational. Then only it is. Then only it can be 0. But again, you can say again it may happen that a flow may be along a streamline. So so it is 0. But again, flow can be rotational as well, right? And the right hand side term is 0. So there is no mentioning of that it is equal to some other term given that the flow is rotational but along a streamline. So there is a possibility that the flow can be incompressible. So we can take this assumption as well. Sorry. This assumption as well. And finally, first incompressible again. This is not valid. Why? Because rho is not taken out of the integration yet. Okay. Rho is not taken out of the integration yet, so it is we cannot say it is incompressible. Again, coming to the doubt of Saurabh, because you may say that we are starting with Euler's equation of motion. You are saying that Euler's equation of motion has to be for incompressible flow. But I'm saying again that for us to be able to solve about the forces that act on the fluid flow on the fluid element only with the momentum equation, we take an assumption that the flow is incompressible. Then only we can disregard the mass conservation equation, the coupling between the mass conservation and the momentum conservation, and only deal with the momentum conservation term to solve for the expression of pressure. Okay, that's one thing to know. But right now there's no explicit mention that we have to disregard the continuity equation completely to be able to find the net force that acts on the body. So with that idea in mind, we cannot, at least for right now, say that the flow is incompressible. Okay, so that's why this case is not possible. So the only correct options are 2, 3 and 5. So option number D. Okay, so I think now Saurabh can also correlate the doubt that he himself asked, so it's implemented in this question. Okay. Yes, thanks Saurabh. So let us look into the next question. So yeah. So the question is, water is flowing through a garden hose. A gardener places a thumb to cover the portion of the hose outlet, causing a thin jet of high speed water to emerge. Okay, again a simple application of the continuity equation. The pressure in the hose just upstream of his thumb is 400 kilopascal gauge pressure. Okay, so if the hose is held upward, what is the maximum height the jet could achieve? Okay, it seems a tricky question, but it's again, I will give you a hint, it's a simple application of the Bernoulli's equation. Okay, but just I'm giving you one good practice. Like, even though if you are applying the Bernoulli's equation, okay, because this kind of question, see, you're given the value of some particular fluid parameter for a particular place, say a particular point in the flow field, and then again one other parameter at the other point, and then you are having to find a correlation between them. So these kind of problems usually in the most simplified manner could be solved using the Bernoulli's equation. Okay, because you are comparing the values of a particular fluid parameter in two different places. Okay, So you can apply the Bernoulli's equation to solve that kind of problem. But before applying it, say this is a MCQ question, so you do not need to show your solution. But say if you're dealing with some subjective type of questions where they say this question itself came to your say mid-sem or end-sem exams, then you need to explicitly show each and every step. Okay, so while doing so, it's a good practice that if you're applying the Bernoulli's equation, just mention why are you able to do so. Mention the assumptions, that is flow is steady, in viscid, constant density, because it's given rho is a constant value, so rho is equal to constant, and say along a streamline. So let me try to draw a schematic diagram. I do not know whether I will be able to do it justice. So say this is the place where the gardener places his finger, okay, and the water is going to a certain height. Let me draw it in a way that I need to only draw the one part. Sorry. Okay. So it is mentioned that the pressure just upstream of the thumb of the so not to be confused, it is the thumb. This is the pipe or hose. Okay, so pressure just upstream is 400 kilopascal. Okay, gauge pressure. You need to find the maximum height up to which the water can reach. Okay, so let us consider, say, this as 0.1 and the maximum height as 0.2. Okay, so pressure at 0.1 is known. So what would be the pressure at 0.2? 0.2 would be basically the atmospheric pressure. Okay, then what about the velocity just below his thumb? Because you are taking the pressure just below his thumb, so what will be the velocity just below his thumb? Did anyone mention? See, let me give you a small, not small, I will say something that I am learning as well, but it's a good practice. Okay, so while you're solving problems using the Bernoulli's equation, a lot of times you will have to deal with approximations. Okay, while, and sometimes it may happen that you may get an answer say 2000 and your friend may get an answer say 1500, but the examiner may give both the answers as correct, given that you have mentioned the assumptions that you have taken while solving the question. Okay, not any vague assumptions, but valid assumptions. Okay, so say if you say that okay, this flow, I can say that if the flow is occurring for a very long time, then I can consider this flow to be steady. Okay, then only it will achieve a constant height. Okay, so flow is steady. First assumption is done. Then I can say that, of course, it's difficult to assume the flow to be in viscid because water itself has a finite viscosity. But given that there are no say walls that are binding the flow and there is no wall present to generate any kind of velocity gradient along this particular say jet of water, then we can say that the flow is in viscid because there is no velocity gradient available. Okay, So more or less the velocity of the fluid will remain constant throughout this jet, and of course will reduce throughout when it reaches as it goes up and reaches a maximum value. Okay, so there is no velocity gradient because of the presence of any walls. So we can say the flow is essentially inviscid. Okay, you need to write these assumptions very specifically for the examiner to know that you are implementing Bernoulli's equation because of these things that you are giving. Okay, Saurabh says it's B. Very nice. Then Saurabh, then can you tell what's the velocity just below his thumb? I asked initially. What did you take it as? Then rho is constant because it is okay. Yeah, Saurabh, please tell.
So just below his thumb.
Yes, because or how could you obtain then your answer? You need to know the velocity, right, to apply the Bernoulli's equation. Or what are the 2 points that you took? You can tell me that. That's also fine.
So I equated the pressure 400 kilopascal and at point 2 I took the pressure as 0.
Yeah, because it's atmospheric pressure. Yeah, and okay, let me just try to visualize what you have written. So it is P1 rho g plus V1 square by 2g plus Z1 is equal to P2 rho g plus V2 square by 2g plus Z2. Okay, so say P2 if it's atmospheric pressure and P1 is gauge pressure, so we can neglect it because it is P ATM, so I will write it is P atmospheric. Then Z1 if I take it as 0, then this can also be neglected. So Z2 is something that we need to determine. And what about okay, and what about V2? V2 would be 0 because at maximum height velocity has to be 0, so this would be 0 at maximum height at Z max. Okay, so what about V1? But because you need to know V1 to get the value of say Z2, right? So what do you take?
So below his thumb, the velocity of water would be 0.
Yeah, exactly. So of course, that's the correct approximation that you have taken. But again, some students may ask like, how is it possible? Because water is striking. Let me draw it. Water is striking his thumb right below it, and then going past his thumb to say purge out of the pipe. Okay, so you may say that the velocity cannot be 0 here, but just below his thumb, okay, just below his thumb at this point where the water strikes his thumb, at this particular point the velocity is 0, right? Say these molecules will hit his thumb and become stagnant, but the other molecules that are along with it may go past it and then come out as a jet, water jet. Okay, but at the point where it hits his thumb, it is 0, right? So if you take a streamline, then comes the concept of along a streamline. So if you take a streamline as such that it passes through that particular point and then comes out as a jet here, and then consider that the point 1 is at this point and point 2 is at the maximum height, then you can take the velocity just below his thumb, so V1 to be as 0. Basically it's a stagnation point. Okay, similar concept will be applied when we discuss the pitot static tube. How we use pitot static tube to measure the velocity, or pitot tube, basically pitot tube for measuring the velocity in a fluid flow. Okay, so with that assumption, if you take V1 as 0, then you can equate this term P1 rho g to this, you will get Z2 as 40.8. Okay, so P1 would be, say, P1 is 400 gauge, so 400 kilopascal, 10 to the power 3, then rho is 10 to the power 3 into 9.81 is equal to Z. If you do this measurements, you will get something like 40.8 meter. So right now it may seem a very vague solution, but it's a very I would say good approximation given that good solution given that we are using such a less amount of effort to obtain the solution. Okay, so that's where the beauty of this kind of simplified form of the governing equations come into picture. Okay, so I think let me just look into it. Which questions can I take? So let me take one more question. I will give you the, for the sake of saving time, I will give you the solution for other questions, because this question is we have taken in the last previous uh, year as well. Otherwise I will just repeat this question. I'm so sorry. I will repeat this question in the next week session. Okay, I hope that's fine. It's an interesting one, but it will take a bit more time to solve it, so I will skip it for now and rather take this question. Okay, this question is a bit interesting because it can be solved easily, but it will take a bit it can be done in a small amount of time, and it's interesting to know about the derivations. Okay, so let's look at question number 5. Okay, this will be the last question. Consider a steady in viscid compressible flow along a streamline. Okay, along a streamline. Assume the fluid to be an ideal gas. Okay, so that P is equal to rho RT holds true. For an isothermal process, which of the following is correct? Okay, so I was telling you about isothermal processes when we are dealing with the rectangular hyperbolas. So that's now what we have here. Okay, so hint would be to start again with the Euler's equations. I will give you idea. So start with the Euler's equation of motion along a streamline. So let me give you the governing equation. Yeah, start with this equation. Okay, so the two terms, these two terms are quite simple to like just simple integration, but the interesting part is this one, how you deal with this term. Okay, so you have P is equal to rho RT. So hint is that substitute the expression for density in terms of pressure and then carry forward the integration. Okay, so rho would be P by RT. Okay, to give you a small hint again, R is the specific gas, universal gas constant. No, it's a specific gas constant. So it's a constant value, and T. Okay, it's isothermal process, so T would be constant. So with all these hints, can you tell me what would be the expression for this kind of flows? Simple substitution of the values. So I will give you 4 minutes. Okay, so Saurabh says it's D. Others, can you contribute? I'll wait for 1 more minute because I think I can take the next question as well. So the answer is correct. Saurabh is correct. Answer is option D, because it's again very simple substitution. So in these two will be just same. It will end up the same, because you can see it is same in all the values. So only thing is that first term would be a bit different, because it is dealing with a variable density now, which has a particular relationship with pressure as from the ideal gas law. Okay. So now if I deal with this term only, so I will have dP by rho is again P by RT, so P dot RT. RT is constant, given that it's an isothermal process, so then only I can take temperature out of the integration. So RT integration of dP by P, it will be R into T ln P. Okay. So now let us look to one more question. Again similar to the previous question. What will be the relation if the flow of the gas is an isentropic one, given by P by rho to the power n is equal to some constant C, where n is a specific heat ratio of the gas and C is a constant. Okay, so all the hints are given. See, these two terms will remain constant. The only thing is this term will vary, because the rho is now a function of it varies with space and has a relationship with pressure. Okay, has a certain relation with pressure. So just do the same thing. It is dP by rho, then P by rho to the power n is a constant. Okay, so rho to the power n would be P by C, or rho would be P by C to the power 1 by n. Just substitute the value of rho here, then tell me what will be the integration. Okay. A bit more involved than the previous question, but same principles. Okay, one more minute, then I will show the answer. It's quite simple. It's a simple integration, but it's a good question for understanding. Oh, okay, Saurabh says it's C. Okay. Okay then, so let us look into the solution. Thanks for trying. Let us see the solution. Maybe okay. Let us do it here itself. Okay, not that maybe I will be able to do it. So it would be integration of dP by P to the power 1 by n dot C to the power 1 by n. Okay, then C to the power 1 by n, it is constant because C is constant. It's mentioned here, right? C is a constant. Integration of P to the power minus 1 by n dP. Okay, C to the power 1 by n. Okay, so C is again P by rho to the power n to the power 1 by n. Integration of P to the power 1 by n would be P to the power minus 1 by n plus 1 divided by minus 1 by n plus 1. Okay, so it would be again P to the power 1 by n divided by rho, because rho to the power n to the power 1 by n would be just rho, then dot P to the power minus 1 by n dot P. Okay, divided by n minus 1 by n. So these two will get cancelled out, so we will left with n by n minus 1 times p by rho. So the correct option would be A. So is that fine, Saurabh? Could you see any mistake? Okay, I thought. Okay then. Sorry, I was not able to complete all the questions. There are some questions remaining, but of course I will share you the solution file, updated notes where it includes all the solutions. Then you can compare with it. Moreover, I will look into the vector identity that Saurabh asked. Then I think it will be good. Okay. Okay then. Thank you so much for attending today's session. Let's all meet next week. And sorry if I was not able to clarify any doubts. I will try to compensate that in the next week. Okay. Thank you then. Thank you everyone. Let's meet next week. Yes. Okay. Thank you.